We're looking at a problem with a car going around a circular turn. The radius of the turn is 50 meters, and the car is traveling at 25 meters per second. The velocity of the car will be constant in magnitude, however, the direction is constantly changing. So we'll have what we call a centripetal acceleration. Remember, acceleration is the rate of change of velocity. So it can be how much the magnitude changes or how much the direction changes. So in a circular motion problem with a constant velocity, the acceleration is how quickly the direction changes. And that formula is centripetal acceleration is equal to velocity squared over the radius. So now I have an equation where I can find the centripetal acceleration of the car. However, I'm interested in the angle that the turn needs to be banked to. So let's draw a cross section of this turn. So this turn is inclined at some angle theta. And I'm also going to add in that there is no friction. We're on a very icy road, so there is no friction between the tires and the road. So notice I've brought up a force. Anytime we're dealing with forces, we need a free body diagram. First force that I notice is acting on the car is gravity. So the weight of the car acting downward toward the center of Earth. The other force I notice is acting is the force normal, or the force acting from the surface, perpendicular. So that is the normal force. You'll see here that we have unbalanced forces, and looking at my circle here, the acceleration is toward the center of the circle. So this car, as it's going around, the acceleration will be this way. So in this situation, unbalanced forces make sense. We have an unbalanced force in one direction, but we have balanced forces in the other. We know that the force is balanced in the other direction because the car isn't jumping up or driving down onto the road. So let's draw a coordinate system that we can use for this problem. So now I've drawn out a coordinate system that we can use. I need to figure out my angles. Using basic geometry, I see that this angle is similar to this angle. So I can see similar angles. Now I can break the normal force into its components in the x and the y direction. So because we're dealing with forces and gravity, we need the mass of the car. The mass of the car will be 1,500 kilograms. I have my normal force broken into components. Now I need to solve the net force in each dimension. I know the car is not accelerating in the y dimension because the car isn't bouncing off the road or getting pushed down into it. Its only acceleration is in the x dimension. So my net force in the y and for simplicity's sake, I'm going to call up positive. So in the y direction, I have the normal force in the y direction minus the weight of the car, and that's equal to 0 because it's not accelerating. In the x direction, I have I only have the x component of the normal force, and that's equal to m times a. And I know that my a is going to be my centripetal acceleration. Let's substitute a couple values in over here in the y. The normal force in the y direction is adjacent to the angle, which means it's the cosine component. So the normal force times the cosine of the angle minus the weight is equal to 0. I'm going to substitute in mg for weight. So the normal force times the cosine of the angle minus mg equals 0. So I'm interested in finding the angle. But I also can substitute in over here. The x component is the sine component. So let's rewrite this one. So when I substitute in the sine, I have the normal force times the sine of the angle is equal to mass times the centripetal acceleration. I don't know what the normal force is. However, I have it in both equations, so I can solve and substitute. So I'm going to solve this equation for normal force. So I've added mg to each side, and now I divide both sides by the cosine of the angle. So now I have the normal force is equal to mg, the weight, divided by the cosine of the angle. I can take this and substitute it in for the normal force over here. So let's do that. So I know m, I know g. I'm looking for theta, but I recognize I have sine divided by cosine, which with our trig rules will tell me that's the tangent. So the tangent of theta times mg is equal to m times the centripetal acceleration. And you'll notice mass shows up on each side, so it cancels. So now I'm going to bring this up here and continue along. So now I have g tangent theta is equal to the centripetal acceleration. But I don't know what the centripetal acceleration is. I know its velocity and the radius. And I know the equation for it. So I'm going to substitute this in for centripetal acceleration. So I have g tangent theta is equal to v squared over r. I know g, it's a constant. I know v, it was given. I know r, it was given. So now I can solve for theta. You'll notice that even though we gave the mass, it wound up canceling out later in the problem. Most problems will do that. So now, let's get theta by itself. I'm going to divide both sides by g. I have tangent of theta is equal to v squared over rg. To undo the tangent, I take the inverse tangent of each side. So the inverse tangent of the tangent of theta is theta, and I take the inverse tangent of the other side as well. So I have theta equals the inverse tangent of velocity squared divided by the radius divided by the acceleration due to gravity. Let's check units. In order to use the trig functions, we can't have any units left over. All the units have to cancel to be able to use a trig function. Let's check that. So unit for velocity is meters per second, and I'm squaring that. So I've squared meters squared per second squared. I'm dividing by the unit for r, which is meters, which is the same as multiplying by 1 over meters. And I'm dividing by g. The unit for g is meters per second squared. So dividing is the same as multiplying by the reciprocal, or seconds squared per meter. And looking at this, seconds and seconds squared cancel out, and meters cancel out. All of my units have canceled out, which means I've probably solved this problem correctly. Let's plug in the numbers and find the angle. So in order for a car to safely take this turn at a speed of 25 meters per second with a radius of 50, the angle the road has to be banked to is 52 degrees. So this is a very high speed in a very narrow circle. which leads to a very high angle. If we start introducing friction, friction acts upwards. We can change our values there, but for simplicity's sake, we're looking at it without friction. This probably isn't a reasonable safe speed for this road because it has to be banked at an angle greater than 45 degrees. So a car that would be on this circular turn safely would be experiencing a banking of 50 degrees. To put this in perspective, the NASCAR tracks that have the highest banking tend to only have banking at about 35 degrees. So we are greatly exceeding the speed which we should be traveling on this road. So hopefully this problem gives you an idea as you're working into your roundabout project. You want to pick a safe speed and you want to look at the radius of your turn so that when you solve your angle, it's a reasonable angle. You don't want an angle of 52 degrees for a roundabout coming onto a school. Probably not a safe turn to take that. So what you want to do is figure out what a reasonable angle is and then maybe work backwards to a radius of turn. That may be the best way to find how big you'll want to make this roundabout. But then you'll also have to consider size constraints and space. Do we have the space to make one that big? If not, there has to be a little bit of give and take each way. It may involve slowing down the speeds. It may involve changing different things about the roundabout. So you have to play with the variables. There'll be some give and take to every variable that you need to consider. Good luck as you're moving forward with this project, and if you have questions, feel free to message or email me. Thank you.